we're going to start with some lectures. All the slides are going to be on Canvas. I still haven't activated the Canvas, but I should have it no later than today or tomorrow. So you'll have it. So whatever you have here, you're going to have it available. All right, so the first thing, as we mentioned, we're going to talk about is we're going to talk about algorithm correctness. How to prove that an algorithm is correct. So sometimes algorithms can be very complicated, but for us, we're going to start with some simpler things than algorithms. We're just going to try to prove some things that are pretty straightforward and understand how proofs work, how logic works, so that we can make good arguments. These arguments can always be applied for any kind of proof. Anything that you want to do to prove something, all of these techniques are acceptable and typically good, rigorous scientific approaches of proving. So proofs are good for non-obvious algorithms, because if an algorithm is true, so why do you need to prove it? It's kind of, everybody can see it's going to be true. But if it becomes a little more complicated, we want to make sure that it's in fact going to be doing what it says it's supposed to be doing. Sometimes when we prove an algorithm, we reveal what we call an inherent strategy or inherent problem. It tells us basically we understand the algorithm better when we try to prove it, because we have to actually go through the steps that the algorithm is doing to show that it is correct. Also, when we look at a proof of an algorithm, we say, well, this algorithm is similar to another algorithm. It's different, but it has a similar approach. So therefore, we can compare, contrast with classes of algorithms, meaning algorithms that are similar or do their work in a similar fashion. For example, this is a greedy algorithm, and this was another greedy algorithm. Okay? Or this is a recursive algorithm that cuts the problem in half in 2 different times, and so is this one. So therefore, they may have a similarity in terms of their proof. And also, once we understand an algorithm, how it's put together, it makes us smarter and better at developing future algorithms. It's nice to use algorithms we already know how to use, but what happens if somebody asks you to come up with something new that doesn't exist? Well, you still have to be able to create it. So it's not enough just to use existing algorithm. We have to be able to come up and develop new algorithms as they are necessary. And the world is changing every day, so we're looking for new algorithms, new solutions. The person who finds the best solution sometimes, is the one that's successful. Okay? So let's talk about the basic idea of proof. So basically, we will look at a proof in 3 different types of proofs. Direct proofs, actually 4, I should say. Direct and indirect, they're really kind of one, direct and indirect. And then we have something called an inductive proof, and then we have a proof by contradiction. The most simple proof technique is the direct proof. So we want to prove something is true, and typically what we want to prove is true is something that looks like this, or we write it like this. Anybody know how you read this? P implies Q. Another way of saying it is if P is true, then Q is true. If P, then Q. Now what does it mean, if P, then Q? If P is true, then Q must be true. Now, P is what? P is what is P? P is a statement. Today is sunny. If I said true or false, today is sunny, you'd look up and say, yeah, it's true. But tomorrow you might say, no. So P could be true or it could be false at different times. Right? I passed the test. True today, false tomorrow. True a week from today. So it changes. The validity or the truthfulness of a statement changes from time to time. P is a statement, but guess what? Q also is a statement. So Q is another statement, and Q again is a different statement which may be true or false. So P can be true or false. Independently, Q can be true or false. They have truth values. P implies Q is called an implication. It's called an implication, and that implication can be true or false. So there are 3 true-false values here. One for P alone, one for Q alone, and one for P implies Q. To prove So to prove that P, the implication is true, you must show that whenever P is true, Q must be true. That's required. So if P is true, Q must be true. Every single time. Cannot fail. If P true, then Q must follow. If that always follows, then the implication is true. What happens if P is true and Q is not true? Well, that means the implication is false. Does that make sense? That means the implication is false, because the implication says if P is true, Q must follow and also be true. If that happens all the time, then the implication is true. If P is true and Q does not follow, the implication is false. Now, what about the situation where P itself is false? P could be false, Q could still be true, and P could be false, and Q could be also false. Well, the implication says if P is true, Q must be true. It doesn't say anything about when P is not true. So when P is not true, the implication doesn't care whether Q is false or true. Therefore, whenever P is false, the implication is true, regardless of the value of Q. So let's apply this to some statements. Okay? Let's apply it to a statement. So let's say if it is a sunny day, then Professor Dichter is happy. That's a smile. That's happiness. Not deep happiness, but happy. You know, good. If it is a sunny day, then Professor Dichter is happy. Okay. So that's an implication. The days change. My mood changes. If that implication is true, and it is sunny outside, then what?
You're happy.
I am happy. So let's say I pull the shades 3 weeks from now, and I'm happy. What does that mean? No. No, it means I'm happy. You see, the implication doesn't say that if it's sunny and only when it's sunny I'm happy. It says if it's sunny, I'm happy. That's it. It doesn't say when I'm happy it's sunny. That's a different thing. Because then I would have very big powers. Wow! Professor Dichter, he's got crazy powers. So that's a very different thing. So therefore, if I'm smiling, he's like, well, so wait a second, we're going to pull the shade. It's raining and he's happy. What's going on? Well, I didn't tell you another implication. If I have a nice lunch, I'm happy. So maybe I just had a nice lunch and I'm happy. That's another condition to be happy. I'm happy when it's sunny. I'm happy when I had a nice lunch. So now, what if I'm happy and I didn't have a nice lunch and it's not? Well, there could be another. Maybe it's payday. Maybe I got a big bonus. Maybe my paper was published in a fine journal, so I'm happy. So many things could make me happy. But if it's sunny, I'm happy. Doesn't say that I'm only happy with. It's not if and only if it's sunny I'm happy. That's a different thing to say. Okay? It's sufficient. Sufficient to make me happy is when it's sunny. But it's not necessary. It's sufficient, but it's not necessary. All right, so that's very, very important. All right, so if we want to prove that P implies Q, if that implication is true, we will assume that P is true, and then use logic and rules of inference, fact going to fact, going to fact, this follows. If this is true, then this must follow. Okay? And if this is true, it must follow, and we must navigate to Q with very small steps to get there. If we can take the truth of P and use the facts that emanate from P being true to drive ourselves to Q directly, then we have proven it directly. Now, indirect proof is very much the same as a direct proof, except that instead of proving P implies Q, that implication, we prove the implication not Q implies not P. Because actually, logically speaking, that is equivalent, logically, exactly to P implies Q. Let's read that backwards from what we have. If I am not smiling, then it is not sunny. If I am not smiling, then it's not sunny. So if I have a face like this. So that is not a smile, right? Not a smile. So that implies that it is not sunny. Because if it's sunny, I must be smiling. I'm not smiling, so it's not sunny. So if I'm not smiling, it's not sunny. But if I am smiling, it may be sunny. Or it may be a good lunch. Or maybe another happy event. Okay, so this is exactly logically equivalent. So therefore, if that's a logic, now we can do, have you guys seen truth tables in a logic class, truth tables? So if you do a truth table for this, how many columns are you going to have? 3 columns. So you're going to have, so for P and Q, you're going to have TT, TF, FT, FF. And then you're going to have tick, 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 tick value for the implication. T, F, 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 F. Now, once you have TT, then not Q and not P is going to be FF. Get the idea? Okay, so you know how to do that. And if you're not, I will introduce you to our good GA next week, and she will show you how to do it. All right, and so therefore, to prove that P implies Q, sometimes it's more convenient to do the equivalent logic proof, which is not Q implies not P. So in that case, we will assume that not Q is true. And then use rules of inference, logic, to step by step to move to show that not P also must be true. Not P means P is false. Not Q means Q is false. Okay? So that's those, and we're going to look at some examples. Now, the next kind of proof is, it's this very powerful proof, especially for some recursive type algorithms and some recursive mathematical statements. Inductive proof, basically, we want to show that some statement is true for, let's say, all positive integers. So let's make the statement P. P of 1 means that P of 1 is true. That means when you substitute the number 1 into the statement, that makes a true statement. Okay? So we want to show that 1 is substituted into P, it makes a true statement. Then we will assume that when you substitute J into the same statement, for values of J greater than 1, but less than some value N, we will assume it's still true. So we'll directly prove for P of 1, and we'll assume for 2 to n minus 1. And then, once we make that assumption, we will show that based on our assumption that P of n must be true, given P of 1 being true, and assuming that P of 2 through n minus 1 is true. If those two things are true, then it implies that P of n is true. How many of you are familiar with proof by induction? So we're going to have to work on that one a little bit. Now, there's a couple of things here. Number one, I will show you how to use the proof by induction. But more importantly, I will later show you why induction is a valid proving technique. Because it sounds like magic, like hocus pocus. How can you prove this directly but just assume this is true? I mean, I can assume anything, right? Yeah, I can assume anything. So therefore, how can I, proving this and assuming something even false, be able to prove this? Because I can assume anything. And you will see that if you assume anything and prove this, and you can show that this is true, then that's actually a complete proof. I will show you, I will validate why induction is a valid technique. And that's kind of a nice, smart thing to be able to know. And the last type of technique that we have is proof by contradiction, also a very powerful proving technique. what we're trying to show in a contradictory proof is to show that some statement P is true. So in order to show that P is true, we will assume, in fact, that P is false. So we will assume P is false. If P is false, that means certain things are going to happen, right? When something is false, that means certain things. So we will use those things and show that assuming that P is false, those elements will drive us to show a contradiction that P is false cannot occur. Since logically P is false, assumption cannot occur, that implies that P is true. Okay, so again, we're going to show you those examples. Okay, so let's look at a direct proof. This is a proof of a statement of n is an odd number or integer if n squared is odd. So this is, if n is odd, then n squared is odd. So the statement, if n is odd, is P. N squared is odd is Q. We're saying if P, then Q. Now how do you prove it? Let's see. If n is odd, so for example, 1 is odd, 1 squared is 1. That's odd. 3 is odd, 3 squared is? That's odd. 5, 25, 7, 49. Okay, prove it, right? No, that's not a proof. What do we call what I just did? Promising, beginning. Sometimes we call it anecdotal evidence. You know what I mean by anecdotal evidence? I saw 4 examples. It was true in 4 examples. Therefore, it must be true for the universe of numbers in the whole. Come on. That's not a proof. What happens if you took a... Do you know what is 1111 squared? Do you know what that number is? No? I don't either. But if you square it, is it odd? Because 1111 is odd. How about 1, 2, 3, 4, 5, 6, 7? That's odd. Square it. Is that odd? Come on. Show them all. You can't show them all. You can't do them all. So we have to have a technique that's going to be able to prove that for all numbers that are odd, no matter how big they are, no matter how small they are, it always will hold true. And the way we're going to do it, we're going to use some basic number theory. So we'll say if n is odd, and we're talking about odd integers here, if n is odd, then n must equal 2 times k, where k is an integer, z is an integer, 2 times some integer plus 1. Because every odd number is 2 times an integer plus 1. Because 2 times any integer makes it even, divisible by 2. Plus 1 must make it odd, because we know an even number plus 1 makes odd. So for example, the number 1 is when k is 0. The number 3 is when k is 1. The number -1 is when k is -1. So we can make if we put every possible integer here, we will get all the possible odd numbers. So all odd numbers can be represented with 2k plus 1, with k being an integer. So therefore, if that's n, 2k plus 1, then n squared is going to be 2k plus 1 squared, the whole thing. And that's going to be 4k squared plus 4k plus 1. So therefore, take an odd number, square it, and you get this. But this can be factored by taking this 1 out and factoring a 2 out of here. You get 2 times this plus 1. But 2 times, this is going to be an integer squared is an integer, times 2 is an integer, plus 2k is an integer. So all the stuff in here is an integer. Times 2 is an even integer. So therefore, when you have that plus 1, it makes it odd. So that shows that for any odd, squaring it produces another odd. So now we don't have to take 1, 2, 3, 4, 5, 6, 7, square it and say, whew, 1, 2, 3, 4, 5, 6, 9, squared. We don't have to do that. This will show us that it's going to work each time. Okay, so let's look at another example. Let's say we want to prove if 3n plus 2 is odd, then n is odd. Now that's a more difficult one because 3n plus 2 is odd, then n is odd. It's going to be a little more difficult, but we can try to prove the indirect proof. The indirect proof is not Q implies not P. That means if n is not odd, then 3n plus 2 is not odd. But if something is not odd as an integer, it must be even, because we only have even or odd integers. We don't have anything in between. So we can restate it. If n is even, then 3n plus 2 is even. Okay, so therefore, we're going to say n is even, so n can be represented by 2k, where k is any integer. And therefore, 3n plus 2 will be simply 3 times the general even integer plus 2, which is going to be 6k plus 2. And then we can take the 2 out, and it's going to be 2 times 3k plus 1. K is any integer. 3k is an integer, plus 1 is an integer, times 2 is an even integer. So that is a indirect proof. Sometimes we call the indirect proof, we call it contrapositive. Contrapositive. So direct proof is P implies Q. Contrapositive or indirect is not Q implies not P. Now, sometimes we have something called a biconditional. The biconditional means that P implies Q and Q implies P. That is in language when we say P if and only if Q. And it means that if P then Q, and if Q then P. That would be the same as saying if and only if it is sunny, Professor Dichter is happy. That means if it's sunny, I'm happy. If I'm happy, it's sunny. Get it? So now, in order to prove that, you have to prove it going forward. You have to prove P implies Q by showing if P is true, you must be able to get to Q. And then you must show if Q is true, you must be able to get back to P. That's a proof for a biconditional. So let's take a look at an example. Given a triangle with sides of length A, B, and C, A squared plus B squared equals C squared if and only if the triangle is a right triangle. Does that seem right to you? It seems right, because we know from the Pythagorean theorem that if we have hypotenuse equal to C in a right triangle, then the length of the two sides squared, the sum of those, is going to equal to the side of the hypotenuse squared. But we want to be able to go forward and backward, if and only if. Okay, so if the triangle is a right triangle, we can use the Pythagorean theorem to show that A squared plus B squared equals C squared. That's a proof. You know why? Because Pythagoras already did it for us. Thank you. Okay, done. Now, in the triangle, the law of cosines can be used to show that any equation, C squared always equals to A squared plus B squared minus 2AB times the cosine of some angle facing C. Right? Where this mu is the angle opposite C. This can only be true when the cosine of u is equal to 0. Because when the cosine of u is equal to 0, this whole term is 0, and you get c squared equals a squared plus b squared. And that occurs only when the angle is a right angle, hence ABC is a right triangle. Does that make sense? So notice that in a biconditional, or an if and only if, we have to go, the proof requires two pieces. You've got to go forward, you've got to be able to go backward. Okay? It's just double the work. Okay, now we're going to look at the proof by induction. So the proof by induction is a proof typically that we can show for, now we're trying to show that basically for all sums where we sum 2 to the power of k, as k goes from 0 to n minus 1, it's going to equal to 2 to the n minus 1 for all integers 0, 1, 2, 3, 4, 5, forever. All non-negative integers, sometimes called whole numbers. So the idea of proving this is going to be divided into the three parts. The basis, which is the proving of the very first initial value, then the assumption, and then the completion step, which uses the first step and the assumption to drive into the general proof. So the basis is going to be, if you take k from 0 to 0, that's exactly one term. That means that k only takes on the value of 0. So the basis says if you go from 0 to 0, that means you only have one element in the sum. 0 to 0, 2 to the k is going to be 2 to the 0 only. And that's equal to 1. And 1 is equal to 2 to the 1 minus 1. So in that case, 1 is equal to 1. Now here, so that's the basis. You see over here, this is nice and true, but it's not necessary. We don't actually have to do this, but I just did it to show you, to give us more happiness. To show you that, okay, now I can use two terms. So if I go from 0 to 1, 2 to the k, that summation is going to be 2 to the 0 plus 2 to the 1. That's going to be 1 plus 2, that's going to be 3. And that 3 is going to equal to 2 to the 2 terms, right? 2 terms here. 4 minus 1 is equal to 3. So you need this for the basis. You don't need this, but sometimes you do it just to make yourself feel like you're on the right track. This looks good. Okay, so now that we've shown the basis for the value of n with one element, we want to do the inductive hypothesis, and that says basically now we're going to generalize the upper bound. We're going to say if you sum the elements, as k goes from 0 to j of 2 to the k, it's going to generally equal to 2 to the j plus 1 minus 1. Okay, again, notice that here the upper index is n minus 1. We add 1 to it to make n minus 1. Since the upper index is j, we add 1 to it to make j plus 1 minus 1. So we basically generalize what we're trying to prove using j, but we limit so that we can go from 0 or higher, but less than n. We're trying to show that it goes for n. N is the general number, so we stop at n minus 1. So therefore, less than n, the biggest integer less than n, n minus 1. So we will assume this. So typically what we do with this step is we take this assumption and we maximize it. Here's how that works. So since I am assuming that this is true for j at the maximum value, what is the maximum value of j according to this limit? N minus 1. So I will plug in n minus 1 into this, and therefore j is n minus 1. Therefore the sum from k equal to 0 to n minus 1 of 2 to the k is equal to j, 2 to the n minus 1 plus 1, which is 2 to the n minus 1. Okay, so now I want to do the whole proof. So I will chop it into two pieces. What I'm going to do first of all, I'm going to say I want to go from 0 all the way to n of 2 to the k. So what I'm going to do is, how many terms are here? From 0 to n is n plus 1, right? From 1 to n, but also 0. So n plus 1. So that means it's the same thing as 2 to the k from 0 to n minus 1, plus just n to n, which is one term. Now, the reason I split them is because this one is covered by the assumption. Because here, I allow j to go up to but not including n, so therefore using the assumption, I can now substitute the value of n minus 1 for j. And therefore, when I plug this into my assumption, this simplifies to 2 to the n minus 1. Does that make sense? Questions? So I'm basically split them here. I split them because here I cannot apply the assumption because the assumption says it must be less than n. You have to limit someplace because you want to show that it's true for any number. So that any number becomes n, and so you can assume only up to n minus 1, then you have to prove for n. So we split from 0 to n, from 0 to n minus 1, and then n to n. But this is split here because of the fact that it maximizes my assumption. So therefore, here the value of j is n minus 1. So therefore, it's n minus 1 plus 1, which is 2 to the n minus 1. There it is. And this term, this is how many terms in this sum? It goes from n and ends at n. So only one value, which is n, and that's going to be 2 to the n. So what we have is 2 to the n minus 1 plus 2 to the n, which is just rearranging them, 2 to the n plus 2 to the n minus 1. That's 2 times 2 to the n, which is 2 to the n plus 1 minus 1. So we have shown that the summation from 0 to n is 2 to the n plus 1 minus n. However, notice that what we're trying to prove is something a little bit different. So, not a problem for us, because basically we can substitute, since we already know this, therefore what we can do is we can, since n is an arbitrary limit, we can allow n to equal n minus 1. And if n is equal to n minus 1, it's going to be 0 to n minus 1, and it's going to be 2 to the n minus 1 plus 1 minus 1, and that becomes 2 to the n minus 1, which is what we're trying to prove. So this proves that this is going to be true for all cases. All right, let's take a look at our proof by contradiction. So we want to prove that square root of 5 is not a rational number. Is not a rational number. What is a rational number? Rational. Ratio. It's like a fraction, right? So a rational number is essentially a fraction where the numerator and the denominator are both what? Integers. Integers. Like 1 over 3. Rational. 27 over 1,000,005. Rational. So integer over integer. Now, we know that rational numbers can be reduced when they are not in lowest terms. So for example, let's say we have a rational number which is 3 divided by 6. But we know that 3 and 6 have a common factor, and that common factor is 3. So we can divide the top by 3 to get 1. We can divide 6 by 3 to get 2. We have 1 over 2. So now we have an integer over an integer, but they have nothing in common except for 1, so they are in lowest terms. So every rational number can be put into lowest terms. For example, 5 over 25 is 1/5. 4 over 5 is what? 4 over 5. Because the prime. 3 over 18, 1/6, etc. So every rational number can be put into lowest terms. So now we want to prove that radical 2 is not a rational number. That's a very hard proof. Because how do you do it directly? It's not a rational number, okay? So it's not. So I want to prove it. Where do you start? Well, we all know radical 5 is a rational number. It is an irrational number. It cannot be expressed as a ratio of two integers. Just like radical 2 is an irrational number. Just like pi is an irrational number. It's a number that is a non-repeating, non-terminating decimal. If you try to approximate square root of 2, there is no finish to it. It just continues going and going and going, just like pi, just like e, just like square root of 7. Okay? So irrational numbers have certain behaviors, but so do rational numbers. If I have a real number which is not irrational, what is it? If it's not an irrational number, it must be a rational number. And if it's not a rational number but it's real, it's irrational. And if it's a real number but it's not irrational, it's rational. Okay, so we have this kind of a binary thing, right? Like odd even, rational, irrational. Now I'm saying real numbers because they're also imaginary numbers, right? Complex numbers. We're not worried about those numbers. We're saying real numbers are either rational or they're irrational. That's it. Because all those numbers are on the real number line. The real numbers, we can know exactly where they are, right here. But the irrational numbers, we can get closer and closer to where they are. We know where they are, but we can drill down closer and closer because they never quite finish their representation. So we have to approximate them. So in order to prove that radical 2 is not a rational number, we're going to use contradiction. We're going to say, let's assume that radical 2 is a rational number, which is basically saying this is p. Radical 2 is an irrational number. We're going to say Radical 2 is a rational number, and that's the negation. So we're saying assume it's false. So we're going to assume that radical 2 is irrational is false. Therefore, our negation is radical 2 is rational. You see what I'm doing here? So now we can use the principles of rational numbers. If radical 2 is rational, then radical 2 is equal to square root of 2 is equal to some integer a over an integer b, where a and b are in lowest terms. Because there must be, for every rational number, you must be able to put it into lowest terms. Just like 5 over 25 is 1/5, 4 over 6 is 2/3, etc., right? So therefore we're going to say, since radical 2 is rational, then a and b must exist, where they are in simplest form, and they cannot be reduced anymore. So we have this situation. So what we can do is we can take this equation, square both sides. Squaring radical 2 gives me 2. Squaring a over b gives me a squared over b squared. And that gives me, by cross multiplication, I get 2b squared is equal to a squared, which says, that implies if a squared is even, then a is even. Now, you might say, wait a second. How do you know if, first of all, if a squared is even, then a is even? How do you know that? How do you know that? Well, believe it or not, we actually proved it before without doing it specifically that way, but we did prove it, and I'll show you why. If a squared is even, a is even. What's the contrapositive of that? What's the contrapositive of this circle? If a is odd, then a squared is odd. We proved that. So therefore, if a squared is even, a is even is true because it's the same proof. It's the contrapositive proof, isn't it? So therefore, so what I'm saying is when we square both sides, we find out that 2b squared is equal to a squared. In that case, a squared must be even. Why? Because it's 2 times some number. So therefore, a squared is even. That implies that a is also even from the previous proof. Okay, so now we know that a is even. That's fine. A can be even, not a problem. So if a is even, let's make a equal to 2k. The general even integer when k is some integer. And therefore, 2b squared is going to equal to 2k squared, which is going to equal to 4k squared. So therefore, b squared is equal to 2k squared, which means that b squared is even, because multiple is 2 times k squared. And if b squared is even, that implies that b is even. So now we have proven that if radical 2 is rational, then we have a must be even and b must be even. But if they're even, then they cannot have no common factors, and we cannot be in lowest terms. So a and b are not in lowest terms. They have a common factor of 2. We said if this is the case, then they will have no common factor for a and b. And what we're seeing here is that no such a and b exists in this case. And because a and b have a common factor of 2, it shows that our assumption that radical 2 is rational has come to a contradiction. Assuming it leads us to a contradiction. Therefore, the assumption cannot hold. If the assumption cannot hold, it must be false. Therefore, radical 2 is rational is false. Therefore, radical 2 is irrational is true. Make sense? So that's how that one works. So that's proved by contradiction. You negate, you make false what you're trying to prove, and show that that leads you to a contradiction, which means you cannot make that assumption because it will lead to a contradiction. So therefore, that assumption is false. Therefore, whatever is the opposite is true. Let's look at this example of proof by induction. So let's go back to our induction case. What we want to show is that n factorial, function factorial, is less than or equal to n to the n power for n greater than 1, where n is any positive integer. What is the smallest value of n based upon these restrictions? 2. So 2 is the smallest one. Okay, what is the value of 2 factorial? 2. What is the value of 2 to the 2?
4.
So, right there, we have just shown, right? We have just shown this is true. 2 factorial is less than 2 to the 2 because 2 is less than 4. That shows the basis. You see over here, I'm also showing 3 factorial is less than 3 to the 3. I made it gray because I'm showing you it's nice, makes you feel good. It doesn't help the proof. But now, if you found that this is false, what would you say? If you found that the gray is false, what would that mean? That means the statement is false. Because if it's true and then it's false for the next case, then it's false. Because you're trying to say it's always true for all these values, 2 or higher. If it's true for 2, but false for 3, no good. Be very careful when you assume certain things, because sometimes you assume, okay, that something is true. I try the first, third, second, third, fourth. Okay, it's true, true, true. It's going to be true. Sometimes when you do some real work, you find out that every once in a while, when you go higher, you start encountering things that are not true. They're just not true. And you didn't expect them, and you're not going to find them because they happen very far away in the future. And future in terms of numbers, like far away from the numbers. But if you make assumptions and you build projects and you build missiles and you build buildings using these assumptions, it's never going to happen. All of a sudden it happens when the numbers get bigger, you could be in big trouble. So it is important to be sure that something that you're saying will always hold true. Okay, so this is sufficient. So our inductive hypothesis will be that, now we'll generalize it. We'll say j factorial less than j to the j, as long as j is greater than 1, less than n. Why less than n? Because we want to show it for n. So we'll stop it at n minus 1, which is the highest integer. By the way, greater than 1 means what's the smallest value of j? 2. But I already showed 2, right? So I could really say greater than, I could say greater than 2. It's not wrong to say greater than 1, but I could really say greater than 2 because 2 has already been proven directly in the basis. The basis is proved directly by plugging in. So now our assumption is going to be this one. So what is the maximizing value of j in our assumption? N minus 1, which means that I will substitute for j n minus 1, so it's going to be n minus 1, the n minus 1 on the right side, and n minus 1 factorial on the left side. So that is my maximizing step from the inductive hypothesis. N minus 1 factorial is less than n minus 1 to the power of n minus 1. What is the smallest value of n possible? Really? But really? No. Because we've already proven this directly, so we don't have to worry about that 2 value. So the smallest value of n really is 3. Okay, 3. So what we're saying is 2 factorial is less than or equal to 2 to the 2. And 3 factorial is less than or equal to 3 to 3. In fact, this is always going to be true up to n minus 1. That's what we're saying. Now, what we're going to do is we're going to try to make this statement right here, make it as close as possible for what we're trying to prove. So you can see that n minus 1 factorial is just n minus 1 times n minus 2 times n minus 3, n minus 4, tick, 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 all the way down to 1. And when I multiply n minus 1 factorial by n, that turns it into n factorial. So I'll multiply both sides by n, and I will get n factorial on the left, which is exactly a match. Why can I do that? Because it's a mathematical. Mathematics allows me to multiply an inequality by a positive number. It's a negative number. They might switch, but I know I'm multiplying by n, and I know n is at least 3. Because if I forgot about that, then I could be proving something not really a smart idea. Okay, so I'm multiplying by at least 3, and that turns the left side to n factorial. The right side is n times this. It's not exactly the same thing as here, right? But let's see what's similar here. What's similar is that on this one, you have n factors of n. N times n times n times n, n times. Here, after multiplying by n, you have one factor of n and n minus 1 factors of n minus 1. But we know that the smallest value of n is 3. That means the smallest value of n minus 1 is 2. So this is either 3 or higher, and this is 2 or higher. Okay. So we notice that if you, so therefore it's not exactly what we're looking for, but look what we can do. We can show that this product, n times n minus 1 to the n minus 1, on the left is going to be less than this one. And the reason for that is because this will also have one factor of n, but all the other factors, where these are at least 2, these are at least 3. So what's going to happen is this is going to be larger, n to the n is larger than n times n minus 1 to the n minus 1. So since since this is larger than this, and we already know that n factorial is less than this value, and this value is less than this value, which is here, then by transitive property, we show that therefore the n factorial must also be less than this one. Does that make sense? So that was a little bit different. You have to do a little thinking for that one, but you get the result is that you're showing, ultimately, you're proving this right here. Any questions? Any questions? Okay, let's look at another example here. So we're gonna try to prove, what kind of tree is this? A binary tree. Okay, looks like a binary tree. We want to prove that a non-empty binary tree. A non-empty tree is a tree that has at least one node. Okay. So we want to prove that a non-empty binary tree with a height of, I'm going to say, I don't have n here, but it's really, I'm using h here, sorry. So height of a tree, how do we count the height of a tree? Well, we look at the deepest path, which is here, and there's two ways of doing it. You can either count the number of nodes from the root to the deepest leaf, 1, 2, 3, 4, which gives us a height of 4. Another way of looking at that is you can say that the distance to the most distant external node, and I'll define external node. Think of all the nodes in a binary tree as internal nodes. Any node in the tree is internal to the tree. So therefore, every node has pointers that go from it to its children. So notice that the pointer here is null and null, 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 and null, null here, right? So if this node did not exist, it would be null and then a pointer. So we think of that null pointer as an external node. So what I mean by that is, so if I wanted to go to the external node from here to the left, I would go 1 and 2. So if I just had this, that would be a tree of height 2. Because the external node is effectively the null pointer. So, all right, so that's fine. All right, so now we want to prove that non-empty binary tree of a height of n has a less than or equal to 2 to the n minus 1 leaves. So we're going to basically do a basis. But before we do the basis, we're going to try to substitute some kind of a mathematical formula for the number of leaves. We're going to let the maximum number of leaves in a binary tree of height n be L of n. So L of n is the number of leaves at most of a tree of height n. L of n, just create a function, L of n. So therefore, what we really want to do, we want to show that L of n is less than 2 to the n minus 1. Does that make sense? So we just create a function name for it. So now L of 1 is going to be what? What is the maximum number of leaves of a tree of height 1? Tree of height 1. So the tree could look like this. So we have L of 1 is 2 to the 0 equal to 1. And it's true because the root in this non-empty tree is also a leaf. So that's a sort of a basic idea. And again, this is optional, but you can say L2 is going to be 2 to the 1, which is equal to 2, which is true, because if a tree has a height of 2, the most leaves it can have is 2. And again, you don't really need to show this, but I'm showing it to you because it may make you feel more confident. So therefore, what we're seeing here is when we have L of 1, it's 2 to the 0, and we have L of 2, it's 2 to the 1. So generally, when we have L to the k, we're going to assume it's less than or equal to 2 to the k minus 1. We're always reducing the parameter by 1, parameter by 1, parameter by 1. So since it was true in the basis, we'll make the assumption. And we'll make the assumption for the height of the tree, k, being less than n. So now, what we're going to do is we're going to maximize our assumption. What's the maximum value of k? n minus 1. So therefore, L of n minus 1 should be 2 to the n minus 1 minus 1. Does that make sense? Okay, so we have L of n minus 1 is less than or equal to 2 to the n minus 1 minus 1, which is n minus 2. So now what we have is this result is by assumption. But really what we want to do is we want to get to L of n, because L of n is what we're trying to show. That's the maximum number of trees of a binary tree of height n. So this is now by assumption, this is the maximum number of leaves we can have. Now, in order for us to grow the tree by 1, if we grow the tree by 1 level, its height will go to n. Because right now it's n minus 1. So each leaf has 0 children at this tree of n minus 1 height. Each leaf can produce 2 leaves. Therefore, Ln, if each of the leaves produce 2, then we'll have 2 leaves for every one of the 2 to the n minus 2 leaves. So it's going to be 2 times maximum number of leaves at n minus 1 height, which will be 2 times 2 to the n minus 2, which is 2 to the n minus 1. And there's the proof. So now we're showing this, showing here. Any questions? All right, so now let's talk a little bit about why induction works. This is my favorite part of induction. You cannot prove induction directly. And you cannot prove induction by induction. You understand that, right? But we can prove induction by contradiction. So this is the most important part of this understanding of why induction is correct. So remember what induction is. Induction is you are trying to prove something is true for all positive integers or for all non-negative integers. So you plug in the first one, you say it's true directly. Then you make an assumption. It's true for the second one through n minus 1. And then you try to use cleverness, ingeniousness, dedication, perspiration to get to n. Got to be logical, got to be mathematical. Okay. So, many theorems state that P of n is true for all positive integers, z plus, positive z. Z is integers. And we use an induction to prove that. So induction says, for example, if we're trying to prove for positive integers, if we know that P of 1 is true, that's the first one, and the proposition P of n implies P of n plus 1 is true for all n, that implies that P of n is true for all n, which are positive integers. So let's see what we're talking about here. What we're doing is, to state it mathematically, we are going to show that the brackets here imply for all n, p of n is true. That's what we're trying to prove. For all n, again, positive integers, let's say. For all n, p of n is true. But in order to prove it, we are using the basis, and the basis says that p of 1 is true. The first one is true. That's the basis. And the second one is our assumption. The second one is our assumption that says p of n implies p of n plus 1. That's really what we're saying. P of n implies p of n plus 1. We're assuming it's true. We're assuming it's true. Is it true? Yes or no? But we're assuming it's true. So therefore, our assumption could be wrong. Or it could be right. If what we're trying to prove is wrong, then our assumption will be wrong, even though our basis could be right. And hopefully, when we put them together, we will not be able to complete the proof. Because that would be fallacious, that would be wrong, right? That would be the wrong thing. So we're saying that if the first occurrence is true, and for every value, if n being true implies n plus 1 is true, that alone implies that it is true for every single positive value of n. That's the powerful thing that we're trying to prove. So, we're going to use something called the well-ordering property. And the well-ordering property is a very simple property. It says that if a set is non-empty and it has non-negative integers, then it has a least element. If a set is non-empty and it has non-negative integers, that means 0, 1, 2, 3, 4, 5, then it has a least element. What's the smallest least element? 0. But if 0 is not in it, what's the next possible least element? What if 0, 1, 2, 3, 4, 5 are not in it? 6 could be there. So basically, now we can't have negatives because we're saying it's going to be non-negative integers, just so it can go in one direction, so we don't have two infinity directions. So every non-empty set of non-negative integers has a least element. So we will assume an argument by contradiction. What we're going to say, p of 1 is true, and p of n implies p of n plus 1, but that does not prove p of n is true for all non-negative n's. So we're going to say, even if you make the true here, and even if p of n implies p of n plus 1, even if those two things are true, they still don't prove it. So what we're saying is, induction is wrong. Induction is not a proving technique. Even if you have the basis, and you have p of n implies p of n plus 1 together, then it does not imply that that's true. So that's what we're going to say. We're going to say, assume it's false. Assume it's false. So we're going to do a proof by contradiction. We're going to try to prove induction by contradiction. So we're going to assume, therefore, there exists, so if induction is false, and even if the basis is directly true, and the assumption is true, it's still not a proof. Well, that means that there must be a case for some value of p sub k for which the thing is false. Because the basis is true. Maybe p of 2 is true, maybe p of 3, but someplace it goes false. And if it goes false once, then the whole thing is not true in general. So we're going to assume there exists a positive integer where p of n is false. Then S, which is a set of positive integers for which p of n is false, is not empty. Because that means the existence of a single value that makes it false, we're going to put that value into S. S is going to contain all the positive integers for which these two things still don't prove it. So we're going to put them into S. Therefore, if we put them into S and we're plugging in basically positive integers, we know 1 is not there because 1 is basis. Therefore, S has a least element, because that least element is the one where the proof fails to be true. Now, K is that least element. K cannot be 1. And the reason it cannot be 1 is because P1 is true by basis. We plugged it in. It's true. Okay? So therefore, K must be greater than 1. What's the smallest element that's not true? K, right? The smallest element for which the proof is not true is K. That's the smallest one, right? So therefore, K minus 1, also a positive integer, by K minus 1 is less than K, so K minus 1 cannot be in S. Since P of K minus 1 implies P of K has shown to be true, then P of K must be true. But if P of K must be true, that's a contradiction that K is the least element of S. And therefore the assumption that those two are not sufficient for induction are false. It implies a positive integer where P of n is false does not exist. Let's look back on this. Let's look back on this. This is the most important part right here. We're going to look at this a little bit one more time. This is the basis. Basis is true. If basis is false, we're done. Basis is true. This is P of n implies P of n plus 1. What is this? That's the assumption and the completion step. Because think about what we do. We say, assume this is true. Assume this is true. And then on the completion step, we assume it's true. If this, then this. Okay, assume this is true. If this, then this. So we have proven, not the whole thing, but we've proven that P of n minus 1 implies P of n. Because we go up to n minus 1, and then we show if n minus 1 is true, then n must be true. So we show that every P of n implies that the one next must be true. That's what our induction does. So therefore, when we do an inductive proof, we do this, and through the assumption and the completion, we do this. Therefore, we show that this is true, and we show that this is true. And so when this is true and this is true, we have proven for all values, because if we try to show that these two can be proven and there is a least value of k, we show that that k cannot exist. So the assumption that this is not sufficient to prove for all n is false, therefore this is sufficient for all n. Does that make sense? And that's why induction is a valid proving technique. Because once you prove this part, and from steps 2 and 3 this part, that proves whatever you're trying to show. That's your proof, that's your... Okay, questions? You guys ready for some homework? Yes! Okay, so Canvas still has been activated? So all these notes are going to be there. I'm going to be posting some homework problems. And the homework problems are going to be basically using these techniques right now. So we're going to try to do the homework, so it's very, very relevant. We should have a GA young lady who's going to work with me. So you'll meet her on Wednesday. Next Wednesday. No class on Monday. You're so good today, I decided to give you a day off and make it a national holiday. That's how powerful I am. And I'm also going to smile and make it sunny too, so everybody can enjoy this. All right, see you on Wednesday.